Unlike ethers, sulfides are a little bit more reactive. One of the reactions that they can undergo is an alkylation reaction with an alkyl halide. For example, dimethyl sulfide, when mixed with iodomethane, will undergo an SN2 reaction as shown here. The sulfur will attack the methyl group, eliminate the iodide, and result in a sulfonium salt with the sulfur having a positive charge. Sulfonium salts are stable compounds that are usually used as alkylating agents. In other words, they're used to transfer an alkyl group. For example, this trimethylsulfonium salt, when mixed with sodium methoxide, will undergo an SN2 reaction where the nucleophile attacks one of the three methyl groups and then eliminates the sulfur and the two methyl groups that are attached to it. As a result, we get a dimethyl ether product as well as a byproduct of dimethyl sulfide. If we start off with an unsymmetrical sulfide, sulfonium salt, the nucleophile, such as sodium ethoxide, will attack the least hinder carbon. In this example, the least hinder carbon is this methyl group. The oxygen will attack that methyl group, eliminate the sulfide that is attached to it. As a result, we get this ethyl methyl ether as well as a sulfide byproduct. The chemistry of the mustard gas chemical agent can be explained by a lot of the reactions we just learned in this section. Mustard gas is a chemical agent that has been used in World War I as well as other conflicts. It is an agent that generates hydrochloric acid and leads to blisters on the skin as well as the lungs of the victim. The way this agent works is by first the sulfur attacking one of the carbons that has a chloride leaving group, forming a sulfonium salt, which then is opened by a water molecule or other nucleophile. This results in an HCl byproduct. The reaction can be repeated again, where the sulfur attacks the other carbon with the chlorine leaving group, forming a sulfonium salt. Water once again attacks the sulfonium salt and forms a final product for the mustard gas, as well as a second molecule of HCl. The essential amino acid methionine is essentially a sulfide, which can react with ATP to be alkylated. The sulfur would attack the carbon here that has a triphosphate group, which essentially behaves like a leaving group. As a result, we produce a molecule called SAM, which is in itself is used as an alkylating agent, and specifically the methyl group here is often transferred to different nucleophiles in our bodies. Here's the structure of SAM. SAM is known as a methylating agent. This methyl group here is a good electrophile for different nucleophiles, such as an amino group on noradrenaline. The amino group will attack the methyl group, eliminate the sulfide as well as everything else attached to it, resulting in a methyl group being transferred and producing adrenaline. Sulfides can be oxidized by mild oxidizing agents such as MCPVA or hydrogen peroxide. For example, if we use one equivalent of MCPVA, we can convert a sulfide into a sulfoxide. The reaction starts by one of the lone pairs on the sulfide attacking this oxygen of MCPVA, breaking the peroxide bond to form a double bond here, using the electrons from the carbonyl to pick up a hydrogen and place it on this oxygen. And then lastly, the hydrogen or the electrons between the oxygen-hydrogen bond will attack the sulfur, producing essentially a double bond between sulfur and oxygen. You may encounter another resonance form of sulfoxides, which has a positive charge on sulfur, a single bond between sulfur and oxygen, and a negative charge on the oxygen. Sulfoxides can be oxidized further with a second equivalent of MCPBA or even hydrogen peroxide. They'll be turned into a sulfone. Here's a second example with methylphenyl sulfide. If we use one equivalent of hydrogen peroxide, it will be oxidized into a sulfoxide. Further oxidation with a second equivalent of MCPBA or hydrogen peroxide will convert it into a sulfone.